Hello, welcome back. In this segment, I will quickly compare Fermat-Euler and Miller-Rabin algorithms. By comparison, I mean I wanted to figure out whether there are any composite numbers that are declared as primes by Fermat-Euler but declared as composite by Miller-Rabin, or vice versa. Any difference, basically. Okay. So what I'm going to do is call both these algorithms on a random number of times. Right? You specify how many times you would like to run m times. Okay. Say m can be 1,000 times, and b is the bit size. Okay, how many bits you would like to have in each of your tests, and number of attempts is basically the number of attempts we talked about during primality testing algorithms. Okay, t-tests. Okay, so with these three arguments, I would like to be able to compare Fermat-Euler with Miller-Rabin and figure out whether there are any differences whatsoever between these two algorithms for random inputs. Okay, I'm assuming the randomness is uniform. I'm using underlying Python library that will give me random bits. I specify give me b number of bits, then it will give me a number made of b bits. Okay, that's basically the idea of this segment. And I'm not going to test even numbers, right? Because we know even numbers are not prime other than 2, so I ignore them. So I'm only counting odd numbers, and I'm checking whether any difference occurs between these two algorithms, Fermat-Euler versus Miller-Rabin. Okay, let's get started with the experiment directly. So we would have to pass three arguments: the bit size, the number of tests, and the number of attempts we would like to make for randomization. Okay, so let's see. Let's start simple. Suppose you would like to have 128-bit numbers, random numbers. Let's test 1,000 of those. In each test, we will allow at most 80 attempts before concluding a number is a prime. Okay, let's see what happens. See, no difference. 0 means no difference. Let's increase the number of test cases to 5,000. No difference again. Let's increase the bit size to 256. No difference again. Let's increase the bit size to 512. And in the interest of time, let me decrease the number 5,000 tests to only 2,000 random numbers. Okay, so it's going to take some time, but not much. It's going to come back quickly. And remember that 80 stands for the number of attempts you would like to try. We talked about it during the previous segments. Okay, no difference again. It's quite interesting that Fermat-Euler is extremely fast compared to Miller-Rabin, yet we don't see much difference for random inputs. Okay, let's increase the bit size again to 1,024. It's going to take a little bit more time. Let's see. Okay, no difference again. And let's select even more larger numbers, like 2048-bit numbers. Okay, let's reduce the random number of tests to 500 because it's just too many to try. I'm going to even reduce it further. We get also no difference. So the main message is that for random inputs, you are very likely not find a Carmichael number, right? Therefore, both Fermat-Euler and Miller-Rabin would correctly declare a composite number as a composite with a very negligible probability as a prime, unless you create a backdoor into the random number generation and try to trick both algorithms. Okay, there are algorithms that would construct primes, pseudo primes rather, that will fool both these algorithms. Okay, that's something that I will talk later, but at this point, my main message is to convey to you that for random inputs, it's difficult to find inputs that are considered as prime by one algorithm and composite by other algorithm, or vice versa. It's not that easy. Okay, thank you. That's all.